Hi, welcome to another lesson for CSEC Physics at EduSolutions Institute. Now, today's lesson, we'll be continuing on our previous lesson of moments of a force. Now, we defined last week that moment of a force is the turning effect that force is caused on an object. So when you apply force onto an object and it causes it to turn, then we say that it has exhibit moments. Now, all we're going to do is to put that into practice and do some questions to demonstrate the use of the formula of moments, which is force times the distance away from the pivot point. Now, let's get into it. Now, the first question here states the principle of moments. Now, we know that moments is a turning effect of a force. And from last week, we learned two conditions that's necessary for equilibrium. And equilibrium means the object is stable, it's not moving. So when all these forces are acting, it is still not moving, right? Now, the second point of the condition is the conservation of moments, which tells us that for a body to be in equilibrium, the clockwise moment is equal to the anti-clockwise moment, and this is only true if no external force are present. So this is the conservation of moments, or the principle of moments, that tells us for a body to be in equilibrium, then the clockwise moment, which means the force that will cause it to rotate clockwise, must be equal to the force that causes it to rotate anti-clockwise in terms of the moment's value, except only when the no external forces are present. Now, let's put the equations and the principle into practice. Now, it says that a student decides to use the principle of moments to measure the weight of a meter roll. He suspended the meter roll from a loop of cotton placed at the 30 centimeter mark, which is right here. So that's your pivot point. And balance the ruler by suspending a 50-gram mass from the 6 centimeter mark. So at the 6 centimeter mark, there was a 50-gram mass. Right? Now, the first question here states, calculate the weight of the 50-gram mass. Now, because we know the mass of the object, we can find the weight by simply multiplying mass times gravity. Now, mass here is in 50 grams, which means we need to convert it to its SI unit of kilograms, which is to divide it by 1,000. And hence, we get 0.050 kilograms. Now we can use that kilograms mass to multiply by the gravitational acceleration of 10 on Earth. We get 0.5 newtons. So what this is actually a force of 0.5 newtons that is being pulled down here. Now the next part says if the weight of the ruler is W, what is the moment of this force about point P? Now we know that moments, first thing is to write our formula, is equal to force multiplied by its distance away from the pivot point. So we don't know the moments, right? We know that they say the force is W, so we're going to replace F with W, and its distance away from the pivot point, right? Which is that to this. We know that it's a uniform object, so its center of mass is at 50, and it's 30 from the pivot and 50, so that is 20. So that is 20 centimeters. And again, we always use our SI units. So we change that to meters by divided by 100. So it's 0.20 meters. Therefore, this would just be multiplied by 0.230 meters. And that would be the moment of the weight of the ruler. Now, next thing is to find what that W value is by using the principle of moments. And the principle of moments tells us that the 0.5 Newton will cause it to rotate in an anti-clockwise moment. So to know which direction it will rotate in, all we do is to continue the force arrow towards the pivot point. So therefore, this gives us an anti-clockwise moment. And the weight of the ruler, we continue that downward going towards the pivot. This gives us a clockwise moment. Now we know the anti-clockwise moment, so now we just use it to find the clockwise moment of the weight of the ruler, right? So the thing we're going to add is that the anti-clockwise moment is equal to clockwise moment. The anti-clockwise moment was already the 0.5 force times its distance away, which is from 6 to 30, which is 24 centimeters. We change that to meters, so we get 0.24. So 24 centimeters to meters is 24 divided by 100, we get 0.24. And then that's equal to the clockwise moment, which would be this part that we just did, W multiplied by 0.20. All right, so when we take our calculator out, we multiply 0.5 times 0.24, we get 0.12 equals to 0.20 W. We need W, so we're going to divide by what is being multiplied by it. So therefore, we get this divided by 0.120, and we get 0.6 Newton. So this tells us that the meter rule has a weight of 0.6 newtons, because that's the arrangement that will make this ruler be in equilibrium with this force pivoted at this point having that weight. All right. Next part is calculate the upward force exerted on the ruler by the action at P. Now, if we go back to P, we notice that at the pivot point, there's a strain. So therefore, there has to be a tension force going up. Let's call it T. They want us to know what is that force. Now, that's where the other condition for equilibrium is used, which tells us that opposing forces are equal. And in this case, the opposing forces would be the tension going up, which is the only one going up in this case, would be equal to the 0.5 added force plus the weight of the ruler. And this is 0.5 plus 0.6, which would give us 1.1 newtons. So there's a 1.1 Newton force acting as a tension force in the string to maintain a balancing effect as well. Now let's go to question 2. So here it says the weight of the arm, which is right here, is 250 newtons, and its center of mass is 2.4 meters from P, which is your pivot point. The mass of M is 0.40 meters from the pivot point. Calculate W, which is the weight of the counterweight. All right. So in this case, we want to find the weight of the counterweight. We don't know its mass. So we have to use the principle of moments, because this object will turn about the pivot point right there. So again, to know what directions each force will go, the 250 carry it towards a pivot point, that is a clockwise moment. And the weight going towards the pivot point, that is anti-clockwise. So therefore, we go with clockwise moment equals to anti-clockwise moment. Our clockwise moment is the force of 250 newtons multiplied by 2.40 distance away, and it's going to be equal to the anti-clockwise moment of the weight of the counter arm multiplied by its distance away, 0.40. So if we multiply the 250 multiplied by 2.40, we get 600 equals to 0.40 times weight. We want to know the weight, so we divide by 0.40, and that gives us that the weight of this would be 1,500, and we always put our unit as newtons. All right, so notice these are very simple questions, right, that utilizes the principle of moments. Now, next question, same type of ruler. Now, this time the object is pivoted at 75. There is a 2 Newton force acting at 95, right? And we have the weight of the ruler acting from the 50. We call that W. Calculate the moments of the 2 Newton force about the pivot point. So this one is very simple. It's just to find the moments, force times distance. It is force is 2 newtons. Its distance is from 75 to 95, which is 20 centimeters, which we're going to change it to meters, which is 20 divided by 100, 0.20 meters. So we're multiplying this by 0.20, which we get 0.40 Newton meter. That's the unit for moments, because Newton is taken from the force, meters is taken from the distance. Now use the principle of moments to calculate W. So now we know that this W will rotate it in this way, which is anti-clockwise, right? And the 2 Newton will rotate it in this way, which is clockwise, which we just found, right? So therefore, what we can say here is that the clockwise moment equals to the anti-clockwise moment, right? Our clockwise moment, which is what we found, 0.40 Newton meter, which would be equal to the weight of the ruler multiplied by its distance from the pivot point, which is from 50 to 75. So that is a 25. Its distance is 25 centimeters. Again, we need to change it to meters by dividing it by 100. So we get 0.25. Right? Then we divide by 0.25. So therefore, the weight would be equal to 0.4 divided by 0.25. We get 1.6. And this would be in newtons. All right. Now let's go to our final question, which states, if we have our uniform ruler again, 50 grams and its center passes at the 50 mark, show that the ruler is suspended by a thread at the 70 centimeter mark, balanced by a weight of W at the 80 centimeter mark. Calculate the weight of the ruler. So we know that the mass of the ruler is 90 grams. So again, we need to convert this to kilograms, which is dividing it by 1,000, 0.090 kilograms. But we don't need mass, we need the weight, which is mass times gravitational acceleration. So 0.090 multiplied by 10, we get 0.9 Newton. Now calculate the moments of the weight of the ruler about the 70. So we know the distance is, the weight is acting from the 50 and it's pivoted at 70. So that's the 20 centimeter distance. Changes to meters, which is 20 over 100, 0.20 meters. So to find the moment, M is equal to F times D. The force would be the 0.9 multiplied by 0.20, and that gives us 0.18 Newton meter. All right, let's continue. What is the moment of the weight about the 70 centimeter mark? So now this is just asking us to write the formula just like the first question for weight, which is at the 80 centimeter mark. So we know moment is equal to force times distance. The force would be the weight, distance is 10 centimeters, which is 0.10 meters. So that is your formula that we would use for the moments of the weight of the mass. Then finally, it is calculate the weight of the value of the weight. So again, that's where we use a principle that says the ruler weight, let's call it WR, would be going in the anti-clockwise moment, right? And the weight of the mass added would be going it in the clockwise. So we know the anti-clockwise one, we just calculated 0.18. So what we do is to say clockwise moment equals the anti-clockwise moment, and the clockwise moment was what we want to find. The anti-clockwise moment is a 0.18. Clockwise moment is the weight multiplied by 0.10. So we divide it by 0.10 and we get the weight is equal to 1.8 newtons. And that would be the weight of the mass added to make this roller balance. So as you can see that all these examples have utilized the principle of moments to aid with finding an unknown. And that's because these objects are in equilibrium. They are not moving once they are set in this position. So that's it, guys. I hope you can have some practice utilizing these questions or utilizing extra questions that you'd have had in your notebook or your textbook. So any questions that you have, you can put it in your chat and I will come and give you some reply to it. So thank you for watching. Hope you understand a little bit more about moments of a force and I'll see you next class. Bye-bye.